Okay, so now we're going to move on to the new lecture notes, and we're going to start with eliminations. So, generally speaking, what is an elimination reaction? Basically, you're going to have your leaving group. It's going to most likely be a halide, very similar to SN1 or SN2. And then you're going to have a base. And in the end, this is your product. This is not the entire steps of each mechanism, because there's two different types of elimination reactions, and each of the two different types have different steps, but this is the overall theme that you're going to see in both eliminations. So you're going to start with your leaving group, and you're going to start with a base, and then you're going to end up with the leaving group leaving, and instead of the base attaching to the substrate, you're going to have a double bond now instead, right here. And then you're going to have the protonated base, and this is your leaving group. It's going to remain as an anion. So generally speaking, they're pretty similar to SN reactions, because in the way that SN reactions run is you have a leaving group, and then you'll have a base, and normally this will come and attack, right? So you pretty much have the same requirements for an SN reaction, so the only thing that's going to force it to undergo elimination other than instead of substitution is you're going to have to add heat, which is usually designated as the little triangle, which I drew here, to get the elimination product. There's two different types of elimination reactions, E1 and E2. We're going to go into O'Connor's notes in a minute, but I wanted to have a little bit of an idea of what we're going to get into, because I feel like he kind of jumped straight into it, and that makes it a little bit confusing. So E1, in general, it's going to prefer a weak base, and it prefers a tertiary substrate because the mechanism generates a carbocation. So I'm going to draw the E1 mechanism for you guys. So step 1 is going to be the loss of the leaving group. And step 2, I'm going to include, actually, we'll do it one at a time. So loss of the leaving group. So I'm just going to draw an arbitrary structure. We'll draw a methyl here too. Okie dokie, so your leaving group is going to be your halide like normal, in this case Br. So you're going to have the electrons move into the Br for it to leave, and you're going to end up with this in an E1 reaction. And in this case, you're going to deprotonate. So normally what you could have, actually not in this case, but you could potentially have a hydride shift in this case, if you wanted to, but it would actually really create the same thing because these are both substituted with a methyl. But what's going to end up happening here, which is different than the SN reactions, is that step 2 is going to be deprotonation. So it's going to pull off a hydrogen adjacent to the carbocation. It could either pull off this hydrogen or this hydrogen. Which one it picks is going to depend on which is going to make the more stable double bond. And I'm going to show you what that means in a second when we get to this step. So step 2, deprotonation. Okay, that's kind of not the best. Okay. So we have OH. You can pick any base in this case as long as it's a weak one. Notice that this one isn't negatively charged, so we have H2O. Okay. So when it pulls off the H, actually I'm not going to do this in red. I'm going to do this in purple. So when it pulls off the H, the electrons from the H are going to enter the molecule, and that's going to form the double bond. So let me continue. like that. So going back to what I was saying before, how this H2O can pull off either of these H's, if it had pulled off this H, the electrons would have went this way and you would have had a double bond here. This double bond is less substituted than this one because this one has 2 methyls on both sides of it, while this one only has a methyl here. So in general, when you're doing E1 reactions, you're going to want it to have the more substituted double bond in your product. And like I said, this is just an intro. We're going to get more into it when we go through his notes. But yeah, this is the intro to E1 reaction. Okay, so now we're going to move on to the E2 reaction. And overall, the E2 reaction is going to require a strong base because it's one step, as you guys are going to see in the mechanism. It's kind of like the counterpart for an SN2 reaction, except you're going to add heat so that you get the E2 product and not the SN2 product. And the leaving group must be opposite or anti, or as O'Connor likes to say, anti-periplanar, to the hydrogen that is being removed. So I'll show you the mechanism and hopefully that will make this make more sense. So let me do that. I'm actually going to make this a little. Okay, so like I said, you're going to have one step. I'm going to show you the way the substrate is going to look. All right, so here's going to be my strong base ethoxide, and then my substrate in this case is going to be let me count my carbons and make sure it matches the example I picked. Okay, perfect. So I'm gonna have a BR up here. Actually, I'm gonna make it down here. Let me redraw that so it's cuter. So this is what I'm going to use as my substrate for this example because it'll make it more obvious when you can see when things are opposite of each other. Okay, so I'm going to redraw this substrate using stereochem designations such as like the wedges and the dashes. So 1 second. So my hydrogen is going to be planar going up into the sky, and then on the other side, I'm going to put my H up here, my CH3 here, and you want your leaving group opposite of the hydrogen that your base is going to be pulling off. So I'm going to put my leaving group on a line because now this and this are anti-periplanar or opposite. And if you draw the Newman for that, the H would be up in the back, CH3 over here, CH3 over here. Let me draw it properly, actually. If we're looking at it, I'm going to do it this way. So H, CH3, CH3, BR, CH3, H. So this is what the Newman would be, where this is the first carbon, and this is the first carbon, this is the second, and this is the second. And as you can see, the H is anti to the BR. And O'Connor will get into this later, so this is just an overview. If this doesn't make sense to you, that's totally okay. We're going to get more deep into it, but I'm just showing you the fact that these are anti to each other. It's easier to see in a Newman. Okay, I'm going to erase now and continue. Oh, I didn't mean to erase the whole thing. I'm going to continue with the mech. Okay. So what happens in a E2 mechanism is your base is going to, instead of attacking this instead of attacking the carbon it normally does here, it's instead going to pull off a hydrogen that's anti to your leaving group. And this is because you're adding heat to it, obviously. So it's going to pull off this hydrogen, and these electrons are going to move down into your molecule, and that is going to force the BR to leave because this carbon will become overcrowded once the new, because there's going to be a double bond forming here. Once the new double bond forms, it's going to kick your leaving group out. Okay. Oops. So your product is going to look like this, where this carbon, I know it's kind of complex to look at because I switched from the stereochem designation back to the regular one, but this carbon is here, this one here, and this carbon is here, if that makes sense. And the electrons that went into this are now in this double bond. Okie dokie. And you're also going to have the Br anion as a side product, and you're going to have the protonated version of the base, which is just this. So that's an EN2 mechanism. Okay, so now we can get started looking at his notes now that we have an idea of what both of these reactions are going to be. Because, like I said, he likes to just jump right into things, and that can be kind of confusing for people. A lot of people like to have an overview, like what is going on in an elimination reaction. It's just really important that you got, I know I didn't make it very clear by drawing out an SN1 in comparison, but it's very important that you guys draw the SN1 next to the E1 on your own, and draw the SN2 reaction next to the E2 reaction on your own, and see why the reagents and the reactions are similar in the sense that they start the same and they both have the same amount of steps. However, because you're adding the heat, you're going to get the double bond product instead of the SN1 product. Cool. Okay, so moving on to his notes. So he starts off by saying it can be considered the reverse of an electrophilic addition. And I'm not sure if he taught you this, but this is what an electrophilic addition is. I'll show you what the mech looks like just in case you're curious, because if he did teach you it, then you definitely need to know. The fact that he's actually bringing it up makes me kind of nervous. So I would, okay, let me pull this over. I'm like technologically stupid, so please don't judge me. Okay, so what happens here is that the double bond, or the electrons from the double bond, actually attack the H, and this moves the Br over. So the H is going to add to the less substituted side of the double bond. So again, don't worry too much about this, because if he hasn't gone too deep into it, it's fine. I'm just giving you it in case you're curious. So the electrons are going to pull the H off of the HBr, and you're going to get this, where the H is added to the less substituted side of the carbon, or double bond. Reason being is because you want the more substituted carbocation. So, and you're going to have the Br anion as your side product. So the next part is pretty easy. The Br anion is just going to add to your carbocation, and you're going to get the product that he shows you, which is just the Br here. So yeah, he's basically just making the point that elimination is in a sense the opposite of this, because you're starting with a double bond and you're getting a halide, but in eliminations you're starting with a halide and getting the double bond. Okay, so then he goes on to say that there are two mechanistic paths, and he shows you an E2 sample reaction overview. So this part over here is the overview, and he goes in to show you the mech. So as we remember from before, the E2 reactions are the one-step reactions, where the hydrogen is anti-periplanar, or just anti to the leaving group. So he goes to show you how the O will pull off the H. The H's electrons will go into the ring, or like the compound in this case. And the Br will be kicked out because it's overcrowded. So as always, there's two H's here. Carbon only wants 4 bonds. So if you're creating a new bond by adding this here, it's going to have to kick something out. The reason it's not kicking out either of the H's is because Br is a good leaving group, which we've already talked about. And then you have the product of the double bond and the Br. Basically what we just went over, but his version of it. So he says the reaction is concerted and its rate is directly proportional to the concentration of the base times the concentration of the substrate. So the only important thing you really need to get out of here is that E2 rates of, I guess just say rate of reaction depends on both the concentration of the base and of the substrate. So going back to this was the base and this is the substrate, just in case that wasn't clear. And that's basically the only thing you need to know. I would also learn the rate law. I would definitely write this down because sometimes he likes to ask for this. So this is the rate law, and it's second order. Basically, all that means is when you're saying second or first order, it's depending on how many second order means it depends on two concentrations. So in this case, because it depends on one, the base, and two, the substrate, that makes it second order. And as always, K is a constant. It doesn't affect the reaction. It's just something you have to include in there. Okay, so he moves on to talk about the E1 mechanism. And the first step of the E1 mechanism is very similar to the first step of an SN1 mechanism, where the leaving group just pops off on its own, leaving the carbocation behind. RDS stands for the rate determining step. So that basically means this is the slow step, which is very similar to the SN1 reaction, where the first step is your slow step, which means that it has the larger hump in the reaction coordinate diagram. Cool. I'm going to give you another mechanism that we'll walk through together, but I'm just going through his. And like I said before, instead of this coming and attacking here, it's going to pull the H. So that's what would happen in an SN1 reaction, just to clarify. The O would come and attach to the carbocation. But in the presence of heat, it's actually going to instead pull the H off, and the electrons from the H are going to form the double bond. So the electrons here pull off this H, and then the electrons from the bond move down into the molecule and form the double bond. And then you have 3 H's on your O, so you have a protonated H2O. Okay. And he says that this is the major product because the minor product would also be if the double bond would form this way, if that makes sense. So if the H was pulled off from one of these carbons, you would get the minor product, which is the double bond forming this way. Cool. He goes to talk about that in a bit, but let's walk through a sample mech. Let me get my life together. Okay, on the side. Actually, I'll just move to another page. So another E1 mech is important to practice and rewrite these out many, many times. So like I said, first step, you're going to have your leaving group pop off. So I'm going to draw this one out in, what is it called, like Lewis form? So that it's more easy to follow exactly what's going on. Okay. So yeah, first step, your leaving group leaves. This is a reversible step. And this is your slow step. Like I said, the exact same thing as saying your rate determining step, which is RDS. Then you're left with your carbocation. And your bromine anion. So that's step 1. Step 2 is going to be your fast step. And your base, in this case, I'm going to use water, because you can use a weak base for E1 reactions. So let me draw this out. So it's going to pull off the hydrogen that is going to give you the more stable double bond. In this case, it doesn't really matter because every single one of these carbons is pretty much equivalent around the center carbon. So I'm just going to draw it pulling off one of these H's. So actually, let me redraw this. And then H2O is going to come. So the electrons from the O are going to come and pull off this H, and then the electrons from the double bond are not from the double bond, from the single bond are going to form a double bond up here. And this is going to be an irreversible step, and it's going to be a fast step. So you'll end up with this as your final product, and H3O plus as your, counter ion for H2O once it picks up the extra H. So this is another example of an E1 mech. Just a reminder that this is 2 steps. You have your carbocation intermediate, you have a weak base. It's very similar to an SN1, but you would add heat, which is the triangle. Okay, so going back to his notes, he continues to show you the minor product that I pointed out. I said it would go this way, but it doesn't matter. If it pulled one of these H's off, it would form this way. Okay. So he says that this path involves 2 steps, the first being rate determining, and the rate is only dependent on the substrate. This is important. I would definitely write this down. The concentration of the substrate, I meant. The rate depends on the concentration of the substrate. Okie dokie. This reaction requires a substrate capable of forming a stable carbocation. Okay, this is also another important point. So to have a stable carbocation, what do you typically need? You can answer that in your head. But basically, you have to be a secondary or tertiary substrate to form a stable carbocation. So again, very similar to your regular SN1 reaction. Yeah, this is a big point. Obviously, I've made this point many, many times, but I'm sure people are going to forget. Watch out for the rearrangements. That's really, really important. Thankfully, in these situations, we didn't really have any, but you may have them in the future. No reaction can form because of planar carbocation. That's not really important. You don't really have to work with cyclics. Moving along. He's making the same point that I gave you guys earlier in the beginning of the slides, that E1 requires a weak base, such as H2O or ROH. Anything that's not an anion is pretty much considered a weak base. Anything without a negative charge, basically. And it requires a polar solvent. This is also something, if you guys are making a chart, I would make sure you write that it requires a weak base and a polar solvent. Eliminations usually result in formation of the more stable alkene. Okay, this I kind of explained to you guys earlier. So when you get your carbocation intermediate, say in this case, you're going to have, or like in the example he's giving you right here. Ooh, where's my thing? Okay, go up. How far did it move? So in the example he's giving you, your intermediate is going to look like this once your BR pops off. And now you have a choice between which H it's going to take. It could either take, it can either take this H over here, or it can pull a hydrogen from here. And like I was saying, it's going to want to pull the hydrogen that's going to result in the more stable product. So if you pull off this H here, you're going to have a double bond here. But if you pull off the other H, you'll have a double bond here. This double bond is more substituted because this is connected to a carbon and this is connected to a carbon. So there's more carbons bonded to this orange double bond. This one, however, is terminal. So all of these are hydrogens here, which means it's less substituted. It's more favorable for the double bond to be bonded to a carbon than to be bonded to all hydrogens. So he shows you that this is your major product and this is your minor. What this means is that major products will still form and minor products will also still form. This will just form in much higher amounts. So say this would be probably around 70% and this would be 30%. Because like I was saying to you guys earlier, this is all in a solution, so you're going to have mixes of everything going on. Okay, moving on in his notes, he gives you another example, this time comparing E versus Z double bonds. So this one is comparing substitution on double bonds, which one is more substituted. This one is comparing Z versus E alkenes. In general, E alkenes are more stable than Z alkenes because the larger groups are opposite of each other. So when you do the Newman projection, there's going to be less interaction between the hydrogens, which is more favorable, as you guys remember. However, on a Z alkene, these ones are going to be closer together, so they're going to be interfering with each other. So if you're given the opportunity to make an E or a Z alkene, you want to go with an E. Okay, so then he says E1 reactions compete with SN1 reactions, and generally products are both formed. So this is another good point that he brings up. That's why you have to use heat. If you give heat in your reaction, you're going to prefer the elimination product. But if you don't have heat, you're going to usually have a mixture. I mean, you're going to have a mixture even with heat, but it's going to be favoring the elimination product. But without it, you're going to be favoring the SN1 product. So yeah, it's just a good point to bring up. It doesn't really matter that much because in an exam, like he's going to tell you heat and you're going to know that you need an elimination product. And if it says no heat, you're going to know that it's an SN1 product. So it's just more of like a fun fact. So eliminations, both E1 and E2 can be formed over SN1 and SN2 by higher temperature. Higher temperature just means the triangle, which just means heat. You know, we've been over this. Okay, so moving on. Okay, so this is what I was getting at with the anti-periplanar or like the E2 reactions must have the substrate in a conformation where the leaving group is anti-periplanar to the hydrogen that is being removed by the base. So let's go back to our E2 mechanism. So in general, the base is going to remove a hydrogen, which is going to let the double bond form. This hydrogen has to be anti the Br. And to know for sure if it is, you should draw the Newman. And if it's not, you have to rotate one of the circles so that they're anti and then do your elimination reaction. So going back to his notes, he gives you a sample reaction and then he gives you the Newman for that reaction. Here, the Br is on the right side, and if you look anti to the Br, you have a methyl. In this case, like he's saying, there's going to be no reaction because the hydrogen has to be anti to the CH3. However, if you rotate your Newman, he rotated the Br and the H. I would be careful doing that. I don't think it's necessary. I would simply rotate the back carbon so that the H moves here, this CH3 moves here, and this CH3 moves here. So you would have something that looks like this. Give me 1 second. Why does it always do that? Okay, my bad. So if you keep the front carbon the same, and you only rotate the back carbon, the H would be here, the CH3 would be down here, and the other CH3 would be here. Here, you can see that these are anti to each other. So now what you can do is your base can come, like he shows, and pull off this hydrogen. These electrons are going to move into the carbon in the middle, and your leaving group is going to leave. In this case, it's Br. I accidentally forgot to write the R. So that's the importance of anti-periplanar and anti. So yeah, the carbon is going to go from sp3 hybridization to sp2 hybridization because all double bonded carbons are sp2, and it flattens out. So here, when it's in its flattened state, you could really see whether or not it's E and Z. Just as like, I guess, a tip, it's easier to look at when you draw it like that. So yeah, basically, long story short, E2 reactions are stereospecific. So say he were to ask you like, oh, what are some features of an E2 reaction? You can mention that as one of the points. Okay, so the next slide, he's giving you another example again. He's saying that there's no reaction here because your leaving group, which is always going to be your halide, is not anti to a hydrogen. It's anti to an R, which basically means the rest of your molecule. R is just a designation for the rest of the chain. So he shows you that there's no reaction unless you rotate it. Here he did it the way that I prefer to do it, where you simply just rotate the back carbon only. So what he did was he rotated the H, all right, I'm going to switch colors. He rotated the H down to here, so the R moved up here, and the CH3 moved over, and you see that here. And then you could draw out the actual reaction, where the base comes and removes the hydrogen, the electrons enter the ring, and the chain, and the Cl leaves. Again, he gives you another example. Okay, so he says, which product is more stable when formed at a faster rate? I'm not sure which product he's referring to. I guess he means the E or the Z alkene. You have to ask him about this one because he didn't mention this in his notes earlier. And I know this slide is from an older lecture because it doesn't match the others. Okay, an actual example. Again, he's just getting through the same thing. I think that's literally the exact same slide. Formation of conjugated systems. Okay, this is another good point. So when you have your double bonds, when you're thinking about major versus minor products, your double bonds would prefer to be conjugated, and what that basically means is that they can resonate with each other. So this one can resonate down, and this can resonate over, or the other way around. This can resonate down, and this can resonate over. So these two double bonds are conjugated, but because these two double bonds are a carbon apart, they have a carbon in between each other, they cannot resonate with each other. That wouldn't happen. So in general, it'll prefer the more stable product. More stable basically means, all right, let me write this neatly. More stable, basically, where'd it go? I apologize. Where am I? What slide am I on? Okay. So for the product to be more stable, it's going to have conjugation. So resonance, basically. It's going to prefer E over Z double bonds, and it's going to want more substitution. So that's how you know if it's going to be the major product. Okay, so in your second example, he's showing you the same thing. Even though this one is more substituted, because this is conjugated, this one's actually preferred over this one. So that's a really important point to make that I actually forgot to mention. So conjugation is more important than E and Z, and more important than being substituted. So I'm going to draw a big arrow. Conjugation over substitution. And then substitution is generally more important than E and Z. Alrighty. Moving along. Okay, Zaitsev rule. Beta elimination favors formation of the more highly substituted alkene. So yeah, the Zaitsev's rule is basically just repeating that it prefers the more substituted double bond. Bulkier bases and steric hindrance favor anti-Zaitsev elimination. Okay, so if you have a base and it's really large, you're going to form the minor product. So let me give you his favorite bulky base. It's called tert butoxide, if I remember correctly, and it looks like this. Oh, I don't know how I did that. So this would be an example of a bulky base, and this will give you the minor product, which is the same as the anti. No one's going to refer to it as the minor, they're going to refer to it as the anti-Zaitsev. So it's important Okay, I can't fit it. But you know what I was trying to say. So it's important that you're familiar with these terms and what they mean. So then he goes on to show you different sized bases and which kind of products that they form. So Hoffman is the exact same thing as saying anti-Zaitsev, just so you know. So you can see as the bases get bigger, the anti-Zaitsev or the Hoffman products increase in percentage. So as a general rule, I'm going to write that on the next page. Bulky base in elimination reactions will form anti-Zaitsev. This is the most common way to refer to it. All right. You know what I was trying to say. Anti-Zaitsev products, which is the exact same thing as the minor product, which is the exact same thing as the Hoffman product. I would just be familiar with all of these terms just in case, but this is definitely the most commonly used term.